In particular, I will talk about advection-enhanced diffusion processes in sea ice. Now, as we all in this room know how sea ice is important, we also need to remember that sea ice is a sensitive indicator for global climate change. Now, advection diffusion processes, such as the thermal transport or the motion of an individual flow, are important for the transport of tracers in the ocean, such as nutrients, salt, and carbon. And all these processes are mathematically modeled by the advection diffusion equation. However, it is key to remember that each of these processes occur on a different length scale. One of the fundamental challenges of modeling sea ice and climate is to account for all the different length scales. In sea ice, as we've seen the last 2 days, we have the ice flows, which range from a few centimeters to 10 of kilometers. And on the other hand, we have brine inclusion, which are on the millimeter to centimeter length scale. What we want to do is to understand how we can take the information we know about the small scale and understand, using that, the effect it has on the larger scale system. So today we'll focus on the thermal transport and the brine inclusions. The brine inclusions on the millimeter scale are laced through the ice, and they are connecting to form channels in which fluid can flow. What we want to do is to obtain bounds on the thermal conductivity in the presence of this fluid flow. And you may ask, why bounds? Why am I talking about bounds and not just going out to the sea and calculating the effective thermal conductivity? Well, it's not that easy, and some mathematical models have been made to express the thermal conductivity. One that is mainly used was introduced in 1971, and this model actually expressed the thermal conductivity as a function of both salinity and the temperature. It is used in a lot of the main climate models. Other climate models are actually using just the first term, 2.03, because why consider the salinity and the temperature if it just complicates things? And one question that we should ask, and it's been asked, is how good is it? So if everyone are using it, it must be good, or at least we hope that it's good. Well, okay. So in 1999, Trudel and his group, they actually went and checked. They checked the thermal conductivity as a function of the temperature. And in the graph, you can see the dots. These are the measurements. Now, they compare it to the most used model for thermal conductivity, which is the dashed line. Okay? That didn't work. So they tried to take this dashed line and just reduce it by 10%. And now it's much better, right? It's a better fit, at least if you look between -7 to -20 degrees. And the thing is that they allow some variation in the results due to the physical measurements. However, if you look above -5 degrees, it really doesn't fit anymore. It's not a small measurement issue. Something is changing. And we should all remember the rule of 5, which actually promised us that above -5 degrees, the sea ice becomes permeable. And what we're going to see today is that this enhancement in thermal conductivity is actually due to the fluid velocity inside the ice. So I will present two models. To start, I will start with this model where we take the advection diffusion equation, which connects the thermal conductivity and the brine velocity field. So in this equation, rho is the bulk density of the sea ice, C is the specific heat, phi is the brine volume fraction, and T is the temperature. Now, kappa naught, the thermal conductivity that we're taking in this model, is the thermal conductivity without the presence of fluid flow. And U is our bulk velocity field, which we assume to be incompressible. Now, just because I am doing math, we're trying to ride on the nice balance between a physical model and an easy-to-solve model. So we're going to non-dimensionalize the system just to make the analysis easier. So we're using the characteristic length scale and time scale of the system and just rewrite it. I don't know where I'm pointing. Rewrite it, non-dimensional. So if we rewrite the advective term as a diffusion term, we can actually reduce this equation into a diffusion term in the temperature, in T. Now we focus on the local property kappa I plus age, where kappa, as I said before, it's the thermal conductivity without the presence of fluid flow. I is the identity matrix, and age is the stream matrix, which actually relates to the stream function of the velocity field V. Now, this matrix is skew-symmetric, which will be helpful later. And what we want to obtain is bounds on the effective expression for this local property. Well, in 1991, Avellaneda and Maida adopted the analytic continuation method for the advection diffusion equation, and they obtained Stieltjes representation for the thermal conductivity. Now, this representation includes a tensor valued measure and the Péclet number, which, Conrad, where are you? There are actually 10 different definitions for the Péclet number, but in this case, we take the Péclet number to relate to the fluid flow. Now, already from this equation, you can see that there is definitely an enhancement in the thermal conductivity as a function of the fluid flow. So this very elegant mathematical formula can be used to obtain bounds on the thermal conductivity using either Padé approximation or variational methods. So we define the Stieltjes function, f of p, and assuming that we know the moments of this measure mu, then we can actually bound it using Padé approximations, and after we bound f, we bounded the thermal conductivity. Well, I just said it, right? Assuming we know the moments, and apparently it's not such an easy task to do. So in some specific cases, specifically for the shear flow case, we can talk about the moments of this measure, and some work has been done in this area, and actually bounds have been found both with using Padé approximations or variational methods. However, for a generic flow, this is not the case. Calculating the moments for a generic flow turns out to be a really difficult problem. And as far as we know, ever since 1991, there was no real analytic progress in obtaining explicit bound for generic flows. So that's our goal. Our goal is to obtain analytic bounds on generic three-dimensional flows. So the first real progress was done by Golden's group, where after a lot of work, and it might seem effortless, but they obtained a new Stieltjes representation for the thermal conductivity. Now, to do that, they use the spectral resolution of the operator I gamma H gamma, where I is the complex number, gamma is the projector into curl-free field, which is we can also write as gradient Laplace inverse divergence, and it's a self-adjoint operator. Now, what's nice about this representation is that it completely separates the material properties, such as the thermal conductivity, from the geometric information of the flow. So, using this representation, we can explicitly express each of the moments of the measure in terms of the fluid flow. So, we consider a BC flow, and once we have a BC flow, we can actually calculate all the moments, or until we get tired amounts of moments. And once we have all the moments, we can obtain bounds for the BC flow. Now, I'm not claiming that a BC flow is a realistic type of flow you will see inside the sea ice. However, and I think someone mentioned it yesterday or today, we assume that whatever flow we have inside the sea ice is a continuous function, which means we can use Fourier series to approximate it, which means that obtaining bounds for a BC flow will be a keystone in obtaining bounds for the general case. So that's what we did. We have the effective thermal conductivity as a function of Péclet number, and we can obtain bounds. So the first two bounds, the lower bound will just be the thermal conductivity without the presence of fluid flow. And the upper bound will use the zeroth moment to obtain the upper bound. Now, if we obtain two more non-zero moments, we can find the next set of bounds. And in fact, we can keep doing it and doing it. And the more bounds that we find, then the bounds are getting tighter and tighter. And it looks like we actually get an expression for the thermal conductivity, at least as a function of the Péclet number. And more bounds. Okay, so that's one model, and we obtained the bounds as we wanted. Then we thought of doing it more realistic. So one thing to do is to consider the sea ice to be a system of two components, a liquid brine and solid ice. And this way to really capture the microstructure of the sea ice. So we consider a three-dimensional domain where where we can separate it into the pore space and the solid space. Now, again, we consider the advection diffusion equation, only now the thermal conductivity takes different values on each domain. So if chi p is the indicator function for the pore space, which means 1 on the pore space and 0 otherwise, I can express the thermal conductivity as a sum of some value kappa p on the pore space plus some value kappa s on the solid space. Another change is that in this model we assume that the volume is localized, so it's restricted to the pore space. Okay, we do the same trick as before. We take the advective term, we rewrite it as a diffusion term, and we introduce this matrix H. And again, H, as before, it's the stream matrix, which relate to the stream function, only now it's restricted to the pore space. In a steady state case, we can get this expression where we need to introduce the variable. So kappa d is the difference between the two conductivities, the conductivity of the brine and the conductivity of the ice. and S will be kappa S over kappa D. Now, if you remember, I mentioned that this H is skew-symmetric matrix, which means that actually the matrix I plus H over kappa D is positive definite. And whoever does spectral theory understands how important that is, because it just means that we can directly go and apply spectral theory. Okay, so we introduced the tensor volume function f of s, and using the spectral resolution of the new operator gamma I plus H over kappa D chi p, we can obtain Stieltjes representation for this matrix F. Gamma is the same operator as before, and using this Stieltjes representation, again, I can obtain an expression for a generic expression for all the moments of the measure. So now all we need to do is to explicitly express each of those moments, and then we can obtain bounds. The same thing we did before. It turns out to be a little bit more complicated than just obtain bounds, but we did derive the first two moments. So the zeroth moment is actually the sum of the volume fraction of the pore space and the average flow inside the pore space. The first moment is the convolution of Green's function with this matrix M, and it turns out that this matrix M is an outer product of a vector W with itself, where this W is so important because it expresses so much. It expresses the boundaries of the pore space. It's express the effect of the stream matrix on the boundaries, and it also has the flow through the pore space inside. So one difference than what we did before, all these moments that we obtain now are actually coupled through this variable S, which means that the more moments that I get, I can actually get better bounds even for the initial bounds. So analytically, we can calculate the bounds. So using these first two moments, we can actually calculate the upper bound, which includes both the thermal conductivity of the brine and the ice. Also, it includes the average flow inside the pore space and the volume fraction of the pore space. Similarly, we can do the same and obtain lower order bounds. So these two bounds are obtained using the analytic continuation method. Now, if we'll be more specific, if you'll give me a specific geometry and a specific flow, then theoretically, I can give you back explicit bounds. So for our toy model, we took a three-dimensional cylindrical tube with a cylindrical tube inside, which is our pore space. So we have the fluid inside and the ice outside, and then we can calculate. And we assume, before we calculate, we also assume that we have shear flow. So in this case, since we're talking about the flow only inside the brine inclusions, basically, a shear flow will be a good representation. In this case, again, we can obtain the bound. So the zeroth moment is actually the volume fraction plus the effect of the, plus the average of the fluid velocity inside. And we can obtain upper and lower bounds on the thermal conductivity. I'm so happy that I'm super quick, so I'm like, I started so late and I'm going to be done. Okay, so to summarize, I presented two methods. Both are using the advection diffusion equation. One is the bulk flow model, where we assume that a BC flow will be a good keystone, at least, to start with. And then we obtain the bounds using Padé approximation. The other model, where we emphasize the microstructure of the sea ice, it was enough for us to use the shear flow, and we used the analytic continuation method to obtain bounds. In both cases, we were able to obtain bounds on the thermal conductivity using these methods. And it's just the beginning, but it does lead us one step closer to understanding how we can use information from the small scale to better understand the behavior of the large scale system. So I want to thank NSF, ONR, and ONR Global for funding this research, and thank you for listening.
Do we have any questions? I'll start.
So sorry.
So with this method, are there any restrictions on the velocity field you feed in other than it being incompressible?
So we do assume it's time independent. We're working on another model that has time dependent flow. But other than that, it should just be incompressible. And three-dimensional.
Any boundary conditions are fine. You can have inflow, outflow. There's no restriction.
Oh, so it depends. So which model? So the second model only talks about the flow inside the brine. So we're not crossing over. But the other model, the first model, we're talking about bulk velocity field, in which case we assume it's some kind of an average velocity field already.
So before we finish up, Danny is going to make a couple of quick announcements.